Так, приветствую вас всех. Hello guys. Okay, we'll start numbers and names number 5. Okay, ready? Everybody's ready?
Yeah.
Okay, today we try to talk about symmetries. Have you heard about symmetries?
Yeah.
You heard that?
Can I ask you to move the mouse, please?
To move?
Мышку,
Oh, yeah.
мышку прям, да, вот там в середине. Okay,
Sure,
yeah,
sure.
that's better. Thank you. We're good.
Okay. Anyway, I'll talk about symmetries a little, okay? So symmetries is a very, very general concept, right? So usually in science, symmetries means a lot. Like, for example, I will explain it later, but for example, the energy conservation law, you know that the energy is not changed while physical processes are going, it is actually a symmetry. And some other things like momentum conservations, angular momentum conservation, lots of things regarding conservation of something. So something that is not changed in the process, it's caused by symmetries. We'll talk about simple symmetries first, and then we'll go a little further. Okay, so symmetry. Maybe the simplest form of symmetry, it is called transition symmetry.
What's transition symmetry? Well, I think I know what it is.
Transition.
What it is.
Transition symmetry. Transition means just movement, right? So if you have somebody here, right?
Oh, yeah, never mind. Now I know what it is.
And then you move it, right? This. Okay? And it's not changed. It's called transition symmetry. Very simple. So when we walk, we are actually applying transition symmetry to ourselves. One to another. You see that nothing is changed in this, usually. But sometimes when you walk long enough, like for example for a couple of years, your size will be growing, right? At least for you. For younger children, you're growing up, right? So from this, you can go to this in, for example, 5 years, right?
Yeah.
But it's still transition symmetry. It's still transition symmetry, but also it includes something else because something is changed. Something is changed and something is not. Your figure is very close. Your face is maybe almost the same, but not the same, but you can recognizable, right? But your size has changed maybe significantly, right? So it is called scale symmetry.
Scale symmetry.
Scale. So just your size has changed, right? So like for example, in the case of the face, right? This is transition symmetry and this is scale symmetry. It's like this. Huh?
Just talking about scale symmetry is when everything is the same but the size is bigger. So when you
just the size. The size is changed, not bigger. It may be smaller or bigger, but anyway, this is called scale symmetry. This is simple symmetries I'm talking about, right? Then the next significant symmetry, it is symmetry. It's called rotation symmetry.
Oh, yeah, I know that one. Oh, and your rotation's easy.
Rotation. So you have a figure, right? Then apply rotation symmetry, and the figure maybe like this. So you're rotated, right? Like clockwise or counterclockwise for a certain angle. This is called rotation symmetry. And this is rotation symmetry in the plane, right? In this plane of our whiteboard, right? But it can be in the space too, right? So in the space, rotation symmetry usually involves what is called axis of rotation. So this is, for example, is some line which is called axis of rotation, right? And it's in 3 dimensions, in 3D, so it's in space. And you rotate something around this axis,
Yeah, I don't get it.
just like this.
Not to get it.
like this, take a look. Do you get
Like
it?
this.
It's like a pole. Imagine it's a pole. Yeah.
So, for example, if we have again a person, right, with the eyes, right? And we have rotation symmetry going like this, right? And we rotate it, if you know degrees, to 180 degrees, half the circle, half the circle. So you will have from the back, right? So you rotate it 180 degrees. Or this 180 degrees, usually called P radians.
Pi.
Oh, pi, sorry, pi. Yeah, pi. So
Pi is the number.
it's the number pi, yeah, but it's an angle actually too. So angle 180 is pi. When you rotate it 360, it's the full circle, right? It will be two pi, right? And in this case, what will change?
Nothing.
Nothing. You still have your face and yes. Question? Yes.
If pi is 80 degrees, then what?
180.
180 degrees? Oh yeah, I thought you said 80 degrees.
No, 180. 180 and 360. 360 is a full circle of rotation, full circle. And 180 is half circle, right?
Yeah.
And also all other angles, of course, right? You can use this and this and that, right? So of course in 3D there's it can be not only one axis of rotation. There could be other axis, right? Like another axis of rotation, and you can rotate this way, right? For example, and if you rotate this way, like 180 degrees, you will have what? You will have a person upside down, right?
Oh.
Oops.
Yeah.
So this is rotation, right? It's another important symmetry. Next important symmetry, it is called, I'm not sure about the scientific term on this, probably mirror rotation or reflection. Antosh, maybe you know? Huh? Maybe you know, Antosh, what is the term reflection or mirror rotation?
For what?
Huh? For mirror.
Mirror, it is reflection, yes.
Reflection rotation, right?
No, just reflection. It's not rotation, reflection.
Ah, yes, right. I'm sorry. I said that. Of course, it's reflection symmetry, right? Or mirror, in other way. So something what we see in the mirror. It's pretty interesting thing. It is actually symmetry which goes like this, like we have a mirror, right? Like from that, like we look into the mirror this way, right? Like that we look at the mirror, right? Like this, and this is the mirror. Look like this. What we'll see in the mirror? We'll see
Version of himself.
yourself, right?
Yeah.
Something like this.
Other way.
Yeah, other way. Other way. So how you, like geometrically or mathematically, how you actually find out what is going on here? You take one point, like the pinpoint of your nose, for example, right? You put a perpendicular. You know what perpendicular means? It's the perpendicular, again, like just to remind you, it's the line, like for example, this is a plane, right?
Yeah.
This is a plane. And you put a line which is totally with the right angle with the plane. So any angle, any way you measure the angle to any line in the plane, it will be right angle. This is called perpendicular.
Oh yeah, for example, when you're proving the...
No question? Understand? What is this? Perpendicular.
Yeah.
It's like if you want to put the nail, right? To put the nail into the wooden plane, right? Into wood surface, right? You should put it perpendicular. And like a nail, and you use the hammer, right? To hit it and to put nail into the wood. So this what is perpendicular, right?
Uh-huh.
So the same thing, you put line, perpendicular line, so this is the right angle, to the mirror and pass it to the same distance. So this distance equals distance B. this distance and these are the same. And this will be a reflection. That's how you you build an image, reflection image.
Sasha, close that.
All right.
Get the wire.
So if you have a distance from the mirror A, the distance from your image behind the mirror from the mirror will be B, and B is equals A. So the same distance for each point. For each point, like for the nose, for the eye, it's the same for the eye, the same for the head, the same for left hand, right hand, everything.
Okay. I have a question. It's an interesting one.
Yes.
If there's distance away in the mirror, which is flat, would you say that we have a parallel universe then? Because if it has distance away in the mirror, that means there would have to be light behind that mirror.
It would be a parallel universe in light if we only have in our universe. If the only particles would be light particles, photons, right? Remember? Light particles are called photons, right?
Yeah.
If our universe consisted only of photons, this will be real parallel universe. But we have other particles, not only photons. We have neutrons, we have electrons, protons, lots of other particles, hundreds actually of them. So it's not a parallel universe. And also this image is behind the mirror, behind. So it does not exist like physically. Actually, it is a so-called, not hallucination, but it's, how do you call this? Virtual image, not real.
It's reality. It's augmented reality.
But believe it or not, you can create real image. So it would consist of real photons, not other particles, but real photons. If you use not parallel mirror, but like for example some curved mirror, like a spherical mirror, like this, okay? And if you try to look into this mirror, interesting enough that the image would be not behind the mirror in some cases, but actually before the mirror, here. The image will be here. And you can measure photons here, can register photons, so it will be like your real, it's called real image actually. It's a real you, but consisted only of photons. Like a photon cloud. Photon cloud. Pardon me? You saw it in Science Museum. Okay, great. This is called real image. So yes, it looks like it's a holographic photo. Actually, do the same thing. They create an image that actually you can even try to touch, but it's because it's photons, you cannot touch them, right? But you can measure these photons with the devices, with optical devices. So it is a real thing. So this is a mirror thing, right? Now. There's one question with the mirror. If you look at the mirror, you will see interesting thing. I will do it again, okay? Now we look at the whole picture from above. From above. So we have us, nose, eyes, right? Here. Your left hand and your right hand, right? From above. Here is the mirror. Here is the mirror, and we will take a look what will be the image. So we do the same thing, perpendicular for the nose, right? Nose will be like this, head like this, head, this, right?
Person from the top. It's a person from the top with a big nose.
Oh, you see, nose is here, right? So you
Not here.
this is the image.
You understand the direction. It's okay.
Yeah, this is the image. The same thing for the hands, right? And take a look. Nose is here, right? So which hand is it for this person?
Right. It's the right.
It's the right. And because you have a heart on your left side, right? Your image will be have a heart where?
On left. Right there.
On the right.
What?
You have on the left, so we'll have on the right.
Oh.
So the image is almost like you, but it's interesting that it's actually somehow inverted, right? Our left hand is their right hand, and and the heart is on the right side of your breast, of your breast. Okay?
Okay. Okay.
You understand that, Katya, right? It's going to be on the
You
other
got the
side.
idea? Now here comes
Guys,
the question, which I probably write it, the question, right? So you see that left changed to right when you look in the mirror, right?
Yeah.
And what do you think will happen with your up? So we actually know with your up and down.
feet and legs. How come left and right switches, but up and down does not?
Exactly. Remember the picture before. There was nothing like this. The head was still up, right?
Down.
And the legs were still down with the image. But the left hand is changed to right, and right hand changed to left.
I know why. I know why.
Okay, you'll talk on this. I'm not asking right now. Okay, you'll talk about this. You discuss it. It's
Oh,
not.
it's for later. It's for later.
It's not an easy question. Think about it. Okay, guys. So
That's a
why
good
is it so? Okay. For the mirror reflection. And now the other pretty useful type of symmetry, it is called central symmetry.
Central symmetry?
Central. Central means that before we used so-called plane of symmetry, right? Well, as a mirror is a plane of symmetry, right? So it's symmetrical relative to the plane of mirror, right? When we're using the plane like a whiteboard, right? We can use an axis of symmetry. It will be the same like a mirror. So we do that, right? So this is axis. On the plane, it's the same. This is called axis symmetry. Axis, just the name, right? And or relative to axis. But central is symmetry which is relative to the point. So center, some point. So how we do create the symmetrical image? We're using the point, like point O, for example, or 0, whatever. This is created like this. Okay, for example, we have some face, right? We do that. We take one point, like the pinpoint of your nose, right? And pass the straight line right through the center. And then continue to the same distance after the center. And this will be this thing, right? Then we take another point, like for example, this point, our cheek, right? We continue it here, and we have it here. And we have our head. We continue here again to the same distance, right? We have it here, right? So if you take a look to this, right, you will see, and this will be here, right? This point, the further point will be somewhere here, right? So you will see this will be something like this, then nose, and then something like this.
Oh wait, are you drawing a telescope? Microscope?
Yeah, actually the lens do that, something like this. Yes, sometimes not. Lens is a little more complex than this, but sometimes they do this thing too. Yes, so that's correct. But you understand, right? What is central symmetry does?
Yeah, we did something like this last year when we were watching the eclipse.
Oh
Solar
yeah,
eclipse. We made a photo. Remember?
Okay, you got the idea, right? It's pretty simple, actually, right? So, so the second question is, can you try to create certain images for a few whatever you choose, like a star, like 5-point star, for example, right? Or a square, or maybe this interesting, create this central symmetry for the serpent moon. Okay?
Yep.
Just this example, that's just for you to train, okay? For central symmetry. Also, you can try the same to do with axis symmetry and some others, but those are easy, right? Mostly. Now, we will try to see how the symmetries are used actually in mathematics. I hope you heard about things that are called functions.
Yeah. Which one? Linear functions or something else?
Yeah, linear functions. Anyway, function as a concept, right, is some sort of machine that actually produce from the variable, like x usually, is called argument, produce something else. This function is a machine, right? Some sort of number machine. It takes x and produces something that we may call some other variable like y. The result, right? Or value. They say value of the function. The result is y. So usually it is named like this. Y equals function of x. Function of the argument x. So we put x here, the value of the x here, and we get the result here. This is the concept of function. Any process that correspond argument to the value. Yes.
Vito was a little bit confused. He thought it was f times x.
Yeah, that's what it looks
No.
like. F of x.
Okay.
No, f of x. This is the concept. This is concept of function. And usually, in the concept of function, usually included correspondence like 1 to 1. 1 to 1. So 1x corresponds to 1y, and 1y back corresponds to 1x.
I don't know what x means. I don't understand that part.
X is a variable.
Kriti is confused about the notation. She thinks it's f times x in brackets.
Oh, no. This is the name of function. This is, yes, this how it.
It means,
no.
It means x is the input, and f is, as Jana said, the machine that operates that.
You may put it like this. You see? This is the hole where x comes, and this is the hole where y out comes. So, and this is the tube or something. Something is done here. X comes here, and transformed comes out here.
Oh, okay, I get it.
You got it?
It's like a formula, like x plus 1. Substitute the x.
Sort of like a program.
X plus 1 is the function.
Sort of like a program. F is the machine that runs the program.
Exactly.
X is the program that is being run.
Right. But yeah, you're right. Yeah. So you get it now, Katya?
Yeah.
Did that explain? Okay.
There's also, if I'm not mistaken, there's also useful, sometimes good to know. I think it's called Polish notation, because it was suggested with one Polish guy. Polish notation is right back. It's inverted. It's written like this. Okay, so like here. So x comes here from left to right. Then it's transformed here, and then the value comes out here. So from left to right.
Okay.
Why it is good? Because you in this case you do not even put the brackets, because you may do not use brackets at all. So they may write it like this: x, f, y. So from x to f to y. And this is another notation for the function. It's rarely used, but it's useful in many cases, especially in programming, certain types of programming, coding. It's called Polish notation. So it's good because you may remove brackets. Okay. So, but anyway. So we have a function, and now some examples of functions. Like you mentioned linear function, right? Linear.
Yeah.
Linear function usually is like this: ax plus b, where a is some number, b is some number, so they called constants, mean that they are not variable, constants, not variables, right? And there's one variable.
They're sort of just loose items.
Which is
Papa
called.
told us about this. Papa showed us this.
Okay, good. Which is called variable argument, right? X plus b, right? And y is the value of a function. Okay, another example is quadratic function or square function. I don't know what's the term.
What?
Square function or quadratic function?
Quadratic.
Huh?
Quadratic.
Quadratic, yeah. So quadratic, you know how to write it, right? Okay. Quadratic function. So the variable is put to the power of 2, and then you got the result. And other powers, like it can be a like x to the power of n, and something like this. Some other useful function, we would not talk about them right now. They are called syntax or cosine. Sine or cosine. Well, why I just named them? Because I'll talk about their plots, their graphics a little later. So let's see, sine and cosine. Okay, now let's talk about the plots of these things, right?
Graph.
Graph. So we have this. Usually it's done like this. You have value here, value function here, and arguments here. So this is called argument axis. This is called value axis or function. Right. So if we talk about linear function, this.
Wait, Papa told me about this.
Huh?
Papa told me about this. For example,
Okay.
if it's f of x, it x is what I forget.
Okay. No problem, because we'll talk about this right away. So you have this function, right? So how to make a graph of it, right? Graph. It's pretty easy. You do. This is a linear function, so you can think that it's a line. Actually, it is a line. You can check it. It's maybe one of the small questions. You can check it by yourself, just giving x some numbers and trying to put it here. Simple numbers are like x equals 0. X equals 0. Put 0 here. What you have? Y means what?
Y equals 0 plus b.
So it is
B.
b. So for example, if it's positive, b is here, right? So you have some point, right? Another thing. You can think about like what is simple. You may use of course x like 1, and this will y will be a plus b, right? If x equals 1, right? But another way is like let's think about what will be x if y equals 0. Now y equals 0. So y equals 0, x will be
0.
No. If x is 0, y is b.
So it means 0 equals x plus b. So from here, x equals?
Who can solve?
B.
No. It's ax equals minus b.
With b move here, will be minus b, right?
Yeah.
And divide by a.
Yeah.
So it will be minus.
Bring b to the other side and divide both sides by a. A bad word is on my tip of my tongue.
Minus 6 over 9?
That's b. That's a b over a.
Oh.
Okay, you play with it. Okay, this is another sample for you. Okay, play with this. So minus b a. So x for y 0 is here. This line is y 0. All this line means that y is 0, right? But x equals minus ba. So somewhere here, minus ba. For example, and the graph for this will be a line that only one line that you can pass through these two dots, right? So this is the graph of any linear function. This is a line. Now, so you can play with it, okay?
Did Papa, can I tell you how it works? You know how it works. So if you get the two coordinates, you put a line through where they both meet, and that's your line for whatever you need it for. Right, Papa?
Yes. Correct.
Now, let's try another function, square function, x to the power of 2, right?
Why is x squared?
X squared. So for x equals 0, it is
Y is what?
x equals 0.
Y is also 0. B. Y is B.
Get to pay attention.
If y equals x squared and x is 0, that means y equals 0. So y equals 0.
Right. So it's this point.
Uh,
So we have this point first, right? Now, x equals 1. Y equals
1. Yeah.
1. So here is 1 and x1, so we do this. That's how we put the point.
Yeah.
Right?
Yeah, and then you put a line through where both of the points meet, and that's your line.
Mm-hmm.
No. It only works for linear
I thought
formulas.
this was a linear equation.
Now, another interesting point is minus 1. Let's x will be minus 1. Y will be
Minus 2. I mean 1. Why is 1? Why is 1? Why is 1? Did the y is 1? Because
y. So y is 1. So it's the point is here, right?
Plus.
Point is here.
Sorry.
So you see minus 1 and plus 1 give the same result.
So you already don't have a line. You see that?
Oh yeah.
You see 3 points. It's not a line. It's sort of a curve, right? Some curve. So now let's try 2.
Y
Y will be
4.
4. So it's 2, 3,
Square.
4. Square, of course. So we do it like this. Again, this perpendiculars, right? You see, all these are right angles here. It's called projections.
Pay attention.
Oh yeah, didn't you told us about projections last time?
Mm-hmm, yeah. So these are projections. And minus 2 again. Will be?
Y is 4. Y is 4. Didn't y is 4 again?
Y is 4 again. So what we see? We see that the points getting what? What
It's like a
would...
mirror image.
Huh?
It looks like a mirror image, sort of.
Yes.
Like
So are they symmetrical relative to this axis, to the y-axis?
Oh my god, what is it called? It's oh man.
Reflection.
No, that's not a reflection.
That is a reflection.
This reflection symmetry, yeah.
Oh wait, no, wait, but one of them is bigger than the other.
Yeah, no, it's a reflection. No.
So
What is this, Katya?
image here or the curve here and curve here looks symmetrical. That's easy, right? Minus and plus all will give the same the same number here, right? So
Yeah.
it is symmetrical. Like for the 3 it will be
Who's positive? Did
for 3 it will be 9, right? Somewhere there. Uh-huh.
But I don't get how that's a reflection because a reflection has to be like the opposite of another object. Yes, that is the opposite of another object. For a second, let me talk.
Yes, okay. Guys, Katya, say it again.
One of them is bigger than the other. That can't be a reflection. It's not bigger than.
No, it's not bigger because see these are points, just points, and the real function, because there are points between this, right? So there are points like this, goes like this, like this, like this, like this, and to the 9. So the real curve is like this, and here it is like this. So this branch of the curve is symmetrical to this branch. That's probably you see, right?
Yeah.
This symmetrical to this. So this symmetrical relative to the axis y, to the y-axis. So it is a mirror or reflection symmetry.
Okay.
You got it, right? Okay. So this is x. Okay, now let's try a little more. It looks like the same, but now to the power of 3.
Oh yeah, easy. That's easy. It'd be minus if it was plus, it would still be plus.
Okay, for what? For 0 again is
0.
0. For 1 it's
1.
1 again. Simple, right? For minus 1,
1. Minus 1.
huh?
Minus 1.
Minus 1. So minus 1 is here, right? So the point is here. And now for 2 it is
8.
8. So so 5, 6, 7. Somewhere here for 2. Somewhere here. And for minus 2 it will be, huh?
Minus 8.
Minus 8. So somewhere here. So it's a little.
Does it look like you could put a line through it?
So if you put a line through this, right? If you put a line, just it will be something like this.
It's not a line.
It's a curve. Sorry, it's a curve, not straight line, right? Of course. And what can you say about this curve?
It is a reflection of the other one.
Okay, it looks like reflection, yeah, because they look symmetrical, really. But what kind of symmetry is it?
Oh, yeah, rotation. Rotation.
Actually, that's true. It is rotation.
Rotation, yes. How many degrees?
Good question. Take a look.
If that's 180. 180.
Right. So if you rotate this or rotate this, yes, this part, right? If you rotate this part here, it will coincide with this. Yes, rotation or what kind of other symmetry?
180 degree transition. Transition. Do the axis.
No. No.
Transition, let's talk about transition. Can you by moving this part somehow coincided with this?
So turning.
Without turning. Transition is no turning, just like transition.
To the left you can.
With the turning, rotation, yes, it coincides. What other symmetry? What do you think?
Well, think of the origin.
0.
Origin?
Yeah. It's
mean-
what?
Axis.
You mean of this point origin? That's what you mean?
Yeah.
Okay, so
No.
I said that.
What was the last type of symmetry that Dad represented?
Central.
central, right?
Yes.
This is central symmetry. And you see what is going on with central symmetry, right? If you with the axis symmetry, when you change the sign of the argument, right? The value will be still the same, right? It will be positive, right? So just the same means the same. It does not change. You change x to minus x, y still is y, right? But here, if you change x to minus x, y becomes minus y.
Yeah.
So this is axis symmetry or reflection, and this is central. So with central symmetry, if you change argument to minus, it changed to minus the value. And in reflection symmetry, when you change to minus, the value is still the same. So you better remember this. This is very important things to remember. Okay. Any question to this?
No.
No? Okay. So now the question.
What is 8 times 8 cubed?
And
That's if it's in brackets or not.
x, y, and for example, 1 minus 1, 1, you see it, huge.
Why not?
Minus 1, right? Like, imagine that we have a circle.
We asked why.
Take a look.
We have a circle.
Yeah.
This is considered to be not regular function because each x, each x corresponds to many y, like here y and here y, right? But still, it has, of course, a certain equation, certain function that actually displays this. So if you have, okay, let this be some r, number r, minus r, here is minus r, some constant, so not variable, right? This is called radius vector, because this is called radius of the circle, right? And there is an interesting equation.
I times r squared. R is radius.
R squared, yes. This is the equation for this function. So
Yeah.
so and the another question is,
Exactly.
can you name all the symmetries? Not now, but for you to think. Can you name all the symmetries of this function? Okay,
Listen,
this is a question.
but Jared, Katya and Vita noted a very interesting thing, Jared.
Yes.
That this x squared plus y squared equals a squared is actually Pythagorean theorem.
Okay, then you may think how it corresponds to it, right?
You know what's the question?
The question is, in a circle, what are the
What are the symmetries? Name all the symmetries that actually apply to this graph?
No, what's the symmetry in that?
Yeah,
Yeah, it's a circle.
but there's more than that though. There are infinite lines of symmetry.
If there is a question, ask question. I just want to give you some
What kind of symmetry?
What kind of symmetry?
Rotational?
Yeah.
No. Just name all of them.
Transition.
Name all of them. All of them. Just for you, for training. Okay. Just name all the symmetries that are actually good for the circle. And just two functions, two examples. Just want to show you some functions, right? This function is called sine, like this. This is
No, that's a function. That's sine.
Look at that, reminds me of ways.
Yeah.
Sin reminds me of syntax, drum coding.
okay. Here is minus p. Here is minus 2 pi. Minus pi. Here is minus 2 pi. So again, this is called sine. And again, symmetries. Find symmetries for this function. And another function, which goes like this.
Circle does not.
Oh yeah. This doesn't have rotation. Oh wait,
It does.
It does. The downer one is a downer. The lower dip is a rotation of the higher bumps.
Now let's forget about others. So just for this. And then, Antosha, you show them another function, cosine, okay?
Okay, we'll do.
And symmetries for this, just because I don't want it to make it too much.
Okay.
Okay. And the last big question. Give me last big question. Those are small. You just talk. The big question is the last big question is. Give me the examples of not to me, to your papa, right? Give me the examples of symmetrical functions on your own.
We'll do it this week. All the homework that we have to do,
Okay.
symmetrical.
Just invent some functions that of your own, and give an example. Okay?
I will explain.
Okay.
Okay, spherical functions. Okay.
That's it.
Thank you very much. This was
Thank you,
awesome.
guys. Oh, some questions maybe. Maybe we still have some questions. Sorry. At the end.
You answered everything, Dada. For you, Papa, what do you mean?
Okay.
Love you. Love you.
Wait, Dada.
How?
Can we see Babu?
You can
Love
see
you.
Babu. Okay, just a sec. Okay, I'll just finish
Love
it
you.
first.